Welcome. In this video I'm going to show you how to calculate the lattice parameter and atomic radius for a hexagonal close-packed structure material from the molar mass, the density and the crystal structure. So we can start with the same old equation which I showed you how to get already in a different video. I will put the link in the description. So first let's calculate the Wigner-Seitz radius, which is basically the following. So you have the molar mass and then you divide it by this thing here. And then the Wigner-Seitz radius is the radius of the sphere whose volume equals to the average volume of an atom. So then we can calculate the Wigner-Seitz volume based on this definition. So we have like numbers of atoms and then just the volume of the sphere. And the first task will be to determine the n, the number of atoms, and not to mix it up with the Na, which is the Avogadro's number, the same old number here. But let's get the n. So I would like to draw the hexagonal cell to you, so you will see what I'm talking about. I try to make it nice. So we have the base and then so something like this. First I show you that this is the lattice parameter, or the edge, base edge basically, and then we have another thing is the height of the prism. So this was basically the base edge. So let's count the atoms. So there is each atom at the corners on this, and there is there are 3 atoms in the body, and then we have 6 atoms here as well. So in the corners of this we have basically like 2 hexagonal bases. So we have 2 of them, and then we have 6 atoms at each, but each atom contributes just with its 1/6 of the volume. So in total this will be just 12 divided by 6, which is 2. And then we have the body, which is 3, just simply 3. And I almost forgot, but we have atoms in the middle as well. So let's call it base. And then this is just half of the atom which contributes. So we have 2 times 1/2. So then this is again 1. So 2 plus 3 plus 1, 6 atoms. So n equals 6. Now we know. And now we would like to calculate the volume of this whole thing here, which is V. And then you just use the formula from the math books. A squared times c divided by 2. So basically you calculate this base times the height of the prism divided by 2. But there is a little bit of a problem. There is this c, what we don't usually know from the material. When we meet a HCP material, we usually know the ratio of C and A. So basically the C over A ratio. And then you can get this number by applying some mathematics on this problem. So I will show you how to get that, but let me introduce a new variable from this. So basically I just say that x equals C over A, and then we express C from this. So C equals x times A, just to make some equations simple in the future. But the question is how to get C over A. And this is a very popular exercise in exams, because you have to use your brain a little bit to set up all the mathematics for this. But yeah, basically we would like to know that how to get this C over A. So if you see that this base can be constructed by 6 equilateral triangles here. It was not my best drawing, but you can see it. So you can see these triangles. So let me draw one of the triangles here. So basically we have the atoms outside on the edge, and then there is an atom inside here. This is the atom from the middle of the base. So all these edges are basically A long. And then since it's an equilateral, let me write it down. Equilateral triangle. So this. Then all of the angles are equal, of course. So this thing is 60 degrees here, and then of course the half of it, let's call it alpha, and that will be 30 degrees. And first let me move to the middle of this triangle, so the middle of the triangle here, and let us call this length as B, and let's connect to the edge, which is here is a right angle. So we cut this edge at the half, so A over 2 is the length basically of this part, and of course the other part is the same. So if we highlight this, then we get a right angle triangle like this. So here is our right angle, here is the alpha, and then we have an A here, which is A over 2 to be precise, and we have B. So then we can express the B from this, because we have B, A over 2, and an angle. So this is the same as cosine alpha equals A over 2 divided by B. And then if we rearrange this equation, then we see that A over 2, so this part, then divided by the cosine alpha, which is cosine 30 degrees, which is square root of 3 over 2. So now we use this, and then we just rearranged, so multiplied by B and divided by cosine alpha, so this equals B. And then if we move forward a little bit and simplify the equation, then we get this. Right? And then we are still aiming for the C over A ratio. So what we can still do is we have another triangle. Let me draw it just to show you the details of the triangle. So let's call this edge B, and let's call this edge A, and let's call this edge C over 2, and then I will show you what is what. So we go back to the hexagonal prism. So what we have is the half of the height here, so that will be C over 2. I hope it's visible. And then we have A, so basically we can connect two atoms, one atom here and one atom out in the edge, and then we are left behind with the B down here. And what we know is that A over square root of 3 squared plus C over 2 squared equals A squared. So this is A, we are aiming for this, and the B was basically this guy here, and C over 2 was this guy here. And then we can just do the math. So A over 2, sorry, I messed this up. So A over 2 divided by 3 plus C squared divided by 4 equals A squared. And then we have A on both sides, so let's divide by A. So we divide by A, and then we get the following: 1 over 3 plus C squared over 4A squared equals 1. So we rearrange, and then we get the following. So 4 minus 4 third, and then this will be equal C squared divided by A squared, and then we just use the common denominator, which is 3. So basically this is 12 minus 12 third minus 4 third, which equals 8 third C over A basically squared. So we just get rid of the square, so C over A is this one. And let me go back here. So we said that C over A is square root of A divided by 3, which equals to 1.633. So if the structure is ideal, then the C over A ratio is 1.63. But the real life is not ideal, so this number can be somewhat different in some cases. So now we know the C over A, so we can do the continuation. So basically we would like to do the following. So W equals to V, so that is 3 times square root of 3, and then we use this x equals to c over a. So a to the third power times x divided by 2, and then this equals, now we know that there are 6 atoms, 4 pi, and we just rearrange everything and express a. So this is 48 pi times 9 times square root of 3 times x, which is the c over a, and then the third power of the Wigner-Seitz radius. So basically we know this because this depends on mass and the density, and then we know the c over a, so we can calculate the lattice parameter. So this is very, very simple. And then if we go back to the just the front view of one of the sides, just so you can imagine. So we have circles here and circles here. Each of them is r, and we know that this distance is a. So basically what we see from here is a equals 2r. So if we continue, r equals a over 2. So we know everything. We can calculate the Wigner-Seitz radius, and then from that we can express the lattice parameter, and then from that we can express the atomic radius. So lattice parameter done, and then we have the atomic or covalent radius. So we know this, and we can go to a very simple equation or very simple example. It will not take too much space, so I get this rectangle for it. So titanium. Now we need 3 details. We need the mass, which is 47.867 gram per mole, and then we need the density, which is 4.506 gram per cubic centimeter, and c over a. We can use the theoretical. I will use that now, but in reality it has slightly different. If I remember correctly, it's something like this. So it's smaller than the real. So first we calculate the Wigner-Seitz radius, and then I got 161.5 picometers, and from that we can get the lattice parameter, and that is 292.2 picometers, and then from this we just basically divide it by 2, we can get the atomic radius, and 146.1 picometer. And if we would like to use the real c over a, then this will be 290 AR picometer, and this will be 147.5 picometers. So there is a small difference, and sometimes it is important to get the perfect number. So sometimes we should use the real one, but if you just want to assume it, or if you get a exam, then you will definitely use the theoretical one. So I think this is the most difficult among the three basic metallic structures. BCC and FCC is very simple, especially BCC. So the face-centered cubic and the body-centered cubic structures are very simple, but the hexagonal is a bit more difficult than those because of the extra C/A parameter. But it's not that bad. So once you can find the correct expression for C/A, then you can calculate anything. So I hope this was helpful, and see you in the next video.